This video is going to be about a neuron. Let's first understand what a neuron is, okay? So for that, let's just use our trusty little friend Google over here and see what a neuron is. And if you Google neuron, here's what you get. It's a part of a brain, and it's a nerve cell, and that is used to send messages. That's what a neuron is, right? And so just because of the fact that it's a part of the brain, right, and what we want to do is build a neural network that imitates a brain. We just use the same terms over here as well in neural networks, okay? So let's talk about what a neuron is for a neural network, okay? If you do that right, then you'll be presented with this equation for how you should encode neuron mathematically, okay? So so this is a bit incomplete, but here is what you would see as an equation, okay? So it would be w naught plus w1 x1 plus w2 x2 plus, you can do this up to some term n that you determined, okay? And this is an equation that would pop up, okay? So let's try to understand this equation a little bit, okay? Why do we use this, okay? So this equation is composed of two parts. Let me separate that out for you. So this part over here, right, and this small other part over here, okay? This thing over here, we call it as a bias, right? And this thing over here, we call it as a linear combination, okay? So let's first talk about this linear combination thing, okay? So over here in the linear combination side, you have x1, x2, and so on up to xn, right? These are what you would call as the inputs, okay? Again, bear with me, this would make sense in a little bit. So and this other guys, this w1, w2 dot 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 and wn, these are known as weights, okay? Inputs and weights. So let's first talk about linear combination. What is a linear combination? Where does this comes from, okay? And you can Google linear combinations, and what you'll find is linear combinations actually comes from vectors, okay? Vectors, the idea of vectors. Why are we using the idea of vectors when we are coding neurons, okay? That's because it's for a mathematical simplicity, and if you Google why this equation particularly is used, you'd probably also find that it's very similar to the way our biology works and blah 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 blah. But most of it is because it's mathematically convenient, okay? And I'll tell you why it's mathematically convenient in a while, but this is what Google tells us about linear combination. So let's search this, and hopefully it does that a little bit quicker, and you'll see a similar kind of equation for linear combinations, okay? So let's try to understand what this is for, okay? Linear combinations. So for this, we are gonna take an example. So let us actually head back to our example of f is equals to ma. I think this should be easy to understand. Okay, so over here let's talk about what are the inputs and what is the output. So that's pretty simple. This guy over here is our output, and these two guys are our inputs, right? Okay, so let me write it this way instead. This is our input, this other guy is our input, okay? We can visualize this as a graph. Okay, let me try to visualize this thing as a graph. So let's take m in the x-axis, a in the y-axis, then you can actually plot some graph out. So 1 2 and 3, 1 2 and 3. There is a point over here. I didn't need that ruler. Let's say this point, okay? So this point, what is the value of that point? And if you see over here, and the x is 2, so m is a 2, the y is a 2, so a is a 2, so you'd know that f is equals to ma, so m is a 2 and a is a 2, you'd get a 4, Okay, does that make sense? So this point over here, this point that I got, right, the value of that point would be a 4. Okay, and you can represent this point in terms of a line from the origin. Okay, and this is the idea of vectors. So now we start talking about vectors as well, but I swear this is very, very easy. Okay, now this line over here, okay, this line or this point over here, if you see, right, for any value of m and a, we can actually plot out this point over here, right? So we can plot out this other point over here as well, this other point over here as well, this other point here as well. So all of these points, right, we can actually plot out using using this graph, right? And a general equation for plotting out, right, all of these points, that general equation is written in terms of a linear combination. Okay, so the way you would write that would be f is equal to w naught, or let's just say w1 m plus w2 a, because a and m are our inputs, right? And this equation right over here would be the linear combination. Okay, linear combination. This equation will give you access to all of the points in the graph over here. Okay, that's what the linear combination is for. Now we already know that force is basically ma, so what should be the value for w1 and w2? Okay, you can think about that for a while and you'd realize that you can keep your w1 to be a 0, and then you can put your w2 be a m. That will still give you f is equals to ma, right? And you could do it the other way as well. You could say w1 is a and w2 is a 0. So for these inputs, right, this guy over here and this guy over here, am I recording over here? Yeah. So for these two guys, you'll realize that this equation over here, so f will give you the value of f is equals to ma. Okay, if you don't believe me, you can just put in the value over here in this equation and you can find that out. So let's say we put in this value over here. So w1 is a 0 dot m, w2 is a m a, so you'll get ma. So that's you still get ma, right? So that's good. So now this thing over here is a generalization. And remember, mathematicians love to generalize. So this is just a generalized formula, okay, this linear combination. But if you look at this thing over here, right, this other equation over here, you have this idea of a bias. Why do you need that? So let's understand this again with this example. So let us say that what I want is my mass, I want it to be 2, okay? Let's say it's a 1, and acceleration is also a 1, but I want my output, okay, force, to be a 2. This is what we want. We want this, and we say that this is what we give you. So this thing is given. Okay, how do you do that? Okay, if you look at this simple equation of f is equals to ma, right, then you'll go crazy, because if m is a 1 and a is a 1, you'll only get a 1. Okay, you'll only get f is equals to 1. You'll never get f is equals to 2. What should you do, right? What's the difference? Okay, for f is equals to 2, if you want f is equals to 2, how much are you missing over here? And that answer is a 1. You're missing a 1 to get that 2. So this thing over here, if I add this term, right, then I would get my expected output of 2, right? So this thing over here would be a bias. Okay, so let's try to understand what that is. Okay, so you can think of this as a as a force that is added. Okay, this can be added maybe due to gravity, right? You have your m is this and a is something, and then due to gravity there is an additional a that will make your force as a 2. So even when your mass is a 1 and a is a 1, you can still get your force to be a 2. Okay, so that's what that bias is for. That is for correcting the output in case if there is some case like this. Okay, so that's why we can write this force. We should always have that term bias. Okay, so w naught plus w1, sorry, m plus w2a, right? And we can do the same thing over here, right? Computation of this bias in this equation as well. So what we are expecting is our force should be a 2, right? We don't know what that is. So what is w1 and w2? We already know that for this case and this case it's going to be true. So let's just take this case. So w0 is a 0, m is still an m, and w2 is a m, you get ma. 2 is equals to w0 plus ma. We know that m should be a 1 and a should be a 1. So what you basically get now is 2 is equals to w0 plus 1 times 1, and you can get w0 is equals to 2 minus 1. So therefore w0 is a 1. So just by adding that term bias, now I have a way to say if m is a 1, a is a 1, and I want the force to be a 2, I can make that force to be a 2, right? Because I have this bias term. So that's why you see this kind of equation with a bias and a linear combination for a neuron. Okay, good. Now we understand this thing about linear combination. Now we understand the bias. Okay, now let's try to simplify this. Okay, because if I say, so I'm taking this equation whole over here again. So if I say something like n is equals to w0 plus w1 x1 plus w2 x2, right? And let's just assume that we only have two inputs, x1 and x2. This equation itself is very complicated, right? So if I wanted to code this, how would I code it? Okay, so it does not make sense. Okay, so we can actually represent this in terms of the tree that we did before for back propagations. Okay, and the reason we want to do that again is we want to find the value for these w0, w1 and w2. Okay, we already know the inputs, so in this case also we already knew the inputs, right? And the only thing we can change over here is the w0, w1 and w2. Now let's go back to this idea, right? So if I change my w0 by some amount, how is my output changing? Remember, you already know what the output is supposed to be. If that is the case, then you can use this idea of turning w0, w1 and w2 and figuring out what is happening to the output. Okay, if the output is less than what you expect, then you want to increase it, right? If it is more than what you expect, you want to decrease it, right? So you can have this idea of turning knobs, and that idea is basically using the derivative, right? And then looking at the derivative and seeing if you should turn the knob up or down if you want to tune that output. Okay, so then what should be the initial values for this w0, w1 and w2? Okay, what it should be, we don't really know that, right? Do we don't really know that, so we just assign it random values. Okay, that's what we do in the start. Okay, now first thing, let's actually visualize, let's actually simplify this long equation into smaller equations. So how do you do that? Very simple. Let's just say a is w1 x1 and b is w2 x2. Okay, so that simplifies this equation quite a bit, and you will end up with something like w0 plus a plus b. You can simplify this even further, and you could say something like c is equals to a plus b. If you do that, your equation will now be reduced to this. Okay, so now to compute n, you just need to have that value of c. And computing c is very relatively easy, right? It's just a simple addition. Computing a and b is also very easy. It's just a multiplication. Okay, so now we can visualize this as a tree that we did before for back propagation, and that would look something like this. So this thing n, right? N is basically an addition of W naught and C. C is basically an addition of A and B. A is basically a multiplication of W1 and X1, I think. Yeah. And B is a multiplication of W2 and X2. Okay. So if you could do this, then you could create this tree. Okay, and remember, the reason we want to create this tree is because now we can use the code that we have coded in the previous video to actually represent this tree, right? So basically what that means is we can represent a neuron in terms of the node code that we wrote over here. Okay, we can do that, right? Because we can represent that as a this tree over here. So that's very simple. So we can do that. Okay, and if you already know about neural networks, then you realize that this is not the entire equation that you use for neural network. You actually pass this thing into something called an activation function. So I'm not going to talk about activation function right now, so I'm just skipping this a little bit, just making it easier mathematically, right? So now we can code this equation over here, right, in terms of nodes. Okay, so let's do it. Let's create those nodes. Okay, what are the things that we need? Okay, we need a W1. I don't know what it's supposed to be. Let's just say it's a 0 for now, or we could just call it 1. I need a X1. Okay, X1 is our input. So let me actually separate our inputs and outputs. So this is our inputs. X1 is, let's say, a 1. Again, realize X1 is, we're just using that example of F is equals to MA, right? Let's just say X1 is a 1. And X2 over here, which is our acceleration, let's say, is a 1 as well. These are our weights. Okay, and W2 is, let's say, a 0, and W0, let's say, is a 1. Okay, and what is our output? Output is our n. Okay, so n is basically W0. So you can look at that over here, right? W0 plus C. So W0 plus C. Okay, what is C? C is A plus B. Okay, and A is basically W1 times X1, and B is basically W2 times X2. It's very simple. One more thing is, now that we can represent this whole thing as this tree, right? We should just say this thing is a node. This thing is a node. This thing is also a node, right? And this thing is a node. This other thing is also a node. So when we calculate that n, we get it in terms of nodes, in terms of a node, which is the value 2. Okay, great. Now over here we have this simple neuron. Okay, now over here, let's say we want no, instead of saying that, let's say that we have more than 2 inputs. Okay, let's say if I have another input of X3, which is a node, let's say 2, and then I would need another weight over here, which is W3, which is another node of some random value that I don't know about. So you realize that as I increase my inputs, this code is not really scalable. I would have to do everything manually. So instead, let's encode it a different way. Okay, so here is how we would encode it. We would encode it as a class, and this is a neuron. Okay, a neuron, def __init. Okay, a neuron can have a number of inputs. Okay, so let's just call that n, and that is an integer pass. So n over here would represent the number of inputs. Okay, so instead let's actually simplify this and let you understand what a neuron we can encode as. So this thing over here, right, this whole complicated tree thing, this was a neuron with two inputs, right? Two input neuron. Instead of thinking about this thing as this whole complex tree, we can just think of it as a single thing that takes in two input, right? And it will give you one output. So one output, okay? And so the input is x1 and x2. We can think of this as m, right? This is a, and it will give you out a output, and that is 4. Okay, let's say. And whatever happens inside this neuron, right, this whole complexity, that's hidden. Okay, so we can think of this as this simple construct. Okay, so if I have n number of inputs, right, so the way you would calculate this output f over here, right, would be to give you the m and the a. That's correct, right? So if I have n number of inputs, right, for this neuron, I should have n number of weights, if you remember. So the number of weights for this linear combination over here as well, you could see, right? For this linear combination, the number of weight is equal to the number of input, and there is this additional thing called as a bias, right? So let's encode that. So let's encode the first thing, that is our bias. Okay, so I have a bias term inside my neuron. I don't know what that bias term should be, so I'm just gonna use it as a random number. So random, right? So self.bias is random dot, oh, it's not from random, it's import random. So random dot, let's say, uniform value from a -1 to a 1. That's the value I'd use for my bias. So it would be values from -1 to a 1. I'll do the same thing for my weights. So my weights would be random. Okay, weight should be a list, right? And the number of items in that list should be n. So the way I do that will look something like this. For I in the range of n, I want the random value dot uniform. There's nothing to be scared about, right? This is just a syntax in Python to generate a random number up to that range of n. Okay, so if I have this code right over here, I can create a neuron n, which is a neuron. Okay, and that would have, let's say, 2 inputs. That's what we want right now, right? So 2 inputs, and done. So I would now get some values for the weights. Okay, so if you look at those weights, I get some random value that's between a -1 and a 1, and every time I run this, right, it's gonna be some new weight. Okay, so that's good. And I could say something like, I want 3 inputs to the neuron. If I want 3 inputs, I get 3 weights for the neurons. So that's working correctly. So that's great. Now what else do we need to encode? Okay, so we want this neuron to give us an output. Okay, so we want this neuron to be able to compute. So let's encode that. So if I want this neuron to compute, I need to give it some inputs, right? So my inputs, I need to give it over here. Okay, and this thing would be a list of integer. Does that make sense? Okay, so that's good. Oh, and one thing I almost forgot is that this bias, this weights, right, we should probably assign it as a node so that we can visualize, so that we can use this tree structure, right, to do the backpropagation thing that we've learned before. So this thing should be a node, and this thing also should be a node, right? And notice something, because in the last video we have already added this r add, r sub and stuff, right? I can still take these inputs to be a list of integer, right? And these lists can interact with these weights. So let me actually code it for you to understand. So if I can just take number of inputs, and then the way you would compute the output would be something like this, okay? So for x in inputs, right? What I want to do is I want to do weight multiplied by x. Okay, what is my weight? Weight is basically the weights at whatever index I'm on right now. So let me just encode it in this way, in the range of the self.n. I should probably have n over here somewhere is equals to n. So in that range I want my w, which is self dot weights at whatever index I am on. I want my x, which is inputs at whatever index I am on, right? And what I basically want to do is I want to do w times x, and I want to store it in some variable. Let's say result, which is a 0. So I take that result, right, and I will add it. So I will add this thing. So it's the same as doing this. So if I have w1 x1, I do a add to w2 x2, right? And then I should probably start that result with the bias. So this should be self dot bias. So what that would do is that would say that my result at the start is w0, and for every iteration that this loop will occur, right? So it will look something like this. In the first iteration, result would be equal to w0 plus w1 x1. In the second iteration, the result would be w0 plus x1 plus w2 x2. Okay, and that will give you the result of the computation, and I can return that result. Okay, so that's pretty simple and done. And I can now do something like n dot compute. Okay, I want it to compute, and I want it to compute for some inputs. So my inputs is basically 1 and 1, let's say. So I give that inputs and I say compute. Okay, and that compute would give you a result. List index out of range. Oh, okay, my bad. That neuron should be 2 input neuron. Okay, so now we get a value of that computation, and we get it to be this guy. Okay, whatever. Okay, so now we have a way to have that neuron and make that neuron compute stuff. Okay, what is the next thing that we should do over here? The next thing that we should probably do over here is we need so this result over here, right? We want it to be some value. Okay, so in our force case, we wanted it to be a 2. Okay, this thing is returning 0 point whatever that is. That's not what we want. We want it to be a 2. So we have to now somehow make that happen. Okay, and how would you do that? So the way you do that is you would tweak w0, w1 and w2 in such a way that for every tweak, right, you'd make the f go near to 2. Okay, that's how you should do it. So what we should do over here is we should take that result, right, and you realize that that result is a node. So that over here in this case would be this guy over here. Okay, that result thing that we got is this node. This is the result. Okay, so what we can do is we can back propagate, and for each of these nodes, right, you will get the gradient. So let's do that. We'll do result dot gradient, back propagate. And when you do back propagation, each of the nodes now will have a gradient associated with it. So now we have a way right? So we have a coding for the neuron, and we are now able to calculate the result for the neuron. Okay, so the next step now would be to take this neuron, right, and then we'd want to tweak the parameters such that our output is exactly the expected output. So we'll see you then.